In the last episode, we talked about encephalization, how the human brain got to be 3 times bigger than that of the other hominids, making us the smartest of the apes, and in fact, the smartest of all animals anywhere ever. The second most important physical trait distinguishing modern humans from the other apes that are still around today is the size and shape of our jaws, because we didn't just lose muscle mass. The frame to support it was reduced too. It didn't matter that we had such little mouths and couldn't bite very hard because we were already relying on technology to hunt and to process our food before we eat it. In fact, the size of our jaws had already reduced at the time of Australopiths, and this led to a problem that we still have to deal with. When the depth of the projected maw of our chimpanzee-like ancestors was reduced to the relatively flat face of Australopiths and the even flatter face of humans, then even though the teeth were smaller too, there wasn't always room for them. We didn't need the third molars anymore because we were eating softer food, but our genes are still trying to cram the same 32 teeth into a much reduced space, and that leads to a high probability of impacted wisdom teeth, which are not only very painful, but can also lead to morbidity and potentially lethal infection. Dentistry is a relatively recent profession. If you couldn't go to a dentist, an infected tooth could kill you. For example, there was a skeleton found in Kenya of a boy who had apparently died of an abscessed tooth. He was a big kid, already 5 foot 3 inches tall at maybe only 9 or 10 years old, but he wasn't Homo sapiens. He was Homo erectus, sometimes called Homo ergaster, and he died 1,600,000 years ago. Now look at how many hundreds of centuries we've had to live with this condition or die because of it before someone finally invented pliers. And that was still centuries before they discovered anesthesia, which was only like not even 200 years ago. Look at all the suffering humanity has had to endure as our mouths get smaller and our teeth are more compacted before we finally figured out how to ease that pain. Unfortunately, some people carry another defective mutation with beneficial effect. The formation of the third molar or wisdom tooth is controlled by a Hox gene called PAX9, which is widely conserved among primates and some other mammals. In fact, ours is almost identical to that of gorillas. And this study shows that a particular heterozygous transversion mutation of the PAX9 homeobox gene, substituting alanine for proline, results in the agenesis of the third human molar, meaning that people with this mutation won't grow wisdom teeth at all, and that's why not everyone has them. If we had never invented dentistry, as most animals haven't, then natural selection would have eventually weeded out wisdom teeth, and people with this PAX9 mutation would have eventually replaced us. But because natural selection is so slow and cruel, being literally heartless and thoughtless, those who are into transhumanism hope to take control of our evolution, eliminating natural selection by using gene editing programs to insert beneficial mutations like this into human embryos to save future generations from having to endure morbidity and oral surgery. There are other important changes that were going on in our mouths too. According to this study, the gracilization and diminution of the chewing muscles is associated with an increased density in the mandibular bone of modern humans for more rigidity without flexation, apparently in response to the low magnitude yet high frequency demands of articulate speech. Because we're flapping our jaws all the time, quite rapidly in minutely precise motions, but not for biting or chewing against any resistance. It's difficult to know exactly when this change happened, but we have some clues. If you examine the inside of your mouth in a mirror to see just how ape-like your teeth actually are, notice that dome shape in the roof of your mouth. That shape affords just a bit of space above the tongue that other apes don't have. The roof of their mouths are relatively flat with their tongue pressed against it, which is one of the reasons they can't make anywhere near the range of sounds that we can. That and their mouths are also too deep to make the same noises we do. Archaic Homo species had more jutting mouths than we have, so their speech would have been less clear, assuming they could speak at all. And just like trying to find the right size passage of air to make a whistle, we needed that little bit of extra space to produce different vowels. The hard palate of Homo erectus was more like that of chimpanzees than ours, so they couldn't have said much. But the older brother of our species, Homo neanderthalensis, and our common ancestor, Homo heidelbergensis, both had that bit of space necessary for complex speech. Humans also have a descended larynx compared to the other apes, which again allows for a wider range of sounds. Adhering to the principle of evo-devo, where the young of two closely related species are more alike than the adults are, and where biological or embryological development parallels evolutionary development, the mouth of a modern human infant is initially like that of the other apes, or infant apes, but as the baby grows, the roof of the mouth or hard palate moves backward toward the base of the skull, and the tongue moves back too until half of it is really in the throat. The larynx descends as well, and this new configuration creates the supralaryngeal airway or supralaryngeal vocal tract, because this is what allows for all of the loquacious sesquipedalian syllabic verbosity that you're enjoying or enduring now. The larynx is made of soft tissue and consequently doesn't fossilize. However, the hyoid bone, which connects to the larynx, does fossilize. Neanderthal remains have been found with an intact hyoid bone that is very similar to that of modern humans. If the hyoid had moved to facilitate speech, then Neanderthals were talking, because there's no other reason for the larynx to descend. Just like there's no other reason for the jawbone to become so dense, unless people were already jibber-jabbering constantly, which it seems they were. That would mean that speech had evolved at least 400,000 years ago, before Sapiens and Neanderthals diverged. So their common ancestor, Homo heidelbergensis, must have had that ability too. And that's just the hardware, the physical mechanisms required for speech. But what about the software? Because there are also genetic mutations that are expressed in the brain. For example, expression of the FOX2P gene underpins the skill of producing minute, complex sonic fluctuations in songbirds, as well as echolocation used in bats and verbal communication among humans. Disruptive mutations of FOX2P can also disrupt the ability of humans to acquire, understand, or express spoken language, because the brain can't figure out how to articulate the mouth to make and combine all those complex configurations of vowels and consonants. Comparative genomics shows that although Neanderthals were morphologically distinct from Homo sapiens on many different characteristics, as we'll discuss in another video, their copy of FOX2P is remarkably similar to ours, though still not identical. There was a little bit difference even there. FOX2P doesn't just control the mental comprehension of what words mean, but more accurately, the skill of motor operation, synchronizing the movements of the jaw, lungs, tongue, throat, and mouth for the coordination of all these subtle movements required for fluent vocalization. Where once experts had the idea that language might have appeared as a result of a single mutation, no unambiguous language gene was ever found. So, like so many things, it's more likely a combination of many genes building on a foundation that was already there. Because even monkeys can, as a matter of necessity, understand body language and read facial expression. And human faces are more expressive than most, especially because the almond shape of our eyes exposes the whites of our eyes, and we can communicate so much just by doing that. How well you understand what someone else is feeling, or what they're likely to do, and more importantly, what they want or need you to do, the more likely you are, or in your progeny are, to survive and flourish in that community. So we already knew how to communicate way before we made up words where this sound now means that thing. And we're not the only monkeys to do that either. African vervet monkeys have uniquely distinct alarm calls specific to whether they're warning about the presence of a leopard or a snake or an eagle. There's a different call for each of these predators because each one requires a different type of response, and the monkeys react to those different calls accordingly. Upon hearing the word for eagle, the monkeys take cover from above. The word for snake gets them out of the grass and up the trees again, and if they hear the call for a leopard, they identify where it is to confront the ambushed predator, usually from the safety of the canopy, of course, so that the leopard knows it's been exposed, at which point they usually gives up and moves on. Different species of monkeys have their own words for things too, or the concept of words, at least simple nouns, the basis of language, evidently already existed maybe 10 million years before we invented verbs too. Thus it seems that the first simple languages, like comprehension of rudimentary grunts that we see illustrated in the classic caveman movies, were created via cultural evolution. Then once any degree of verbal communication existed at all, it was so immediately advantageous in all applications that there was a profound selective pressure favoring those genes that enhance and improve our ability to speak and to understand languages. It's called coevolution because our culture prompted, guided, and reinforced the genetic evolution of our linguistic ability. Then our languages evolved too. Experimental studies of real and artificial languages show that their usage changes over time to become easier to learn. Linguistic evolution is analogous to biological evolution in that new words, slang terms, contractions, and so on accumulate in divided factions until one original language has multiple accents, and they continue to grow apart, with each developing their own dialects until they eventually become two distinct languages, where the two no longer understand each other. just like when biological subspecies can no longer interbreed and become different species. The evolution of language is also a good analogy to explain how biological evolution works on the population level rather than at the level of individuals. My favorite example of that is where Latin-speaking people moved to different areas of southern Europe, and then over time, in isolation, their use of Latin eventually changed into Spanish, French, or Romanian through the process of cladogenesis. Whereas those who stayed in Rome changed Latin into Italian via the process of anagenesis, where the new language eventually replaced the old over many centuries of subtle changes, so that there was never a first person to speak Italian, wandering amongst a bunch of Latin speakers. No one in Italy or anywhere in Europe even noticed when one language changed into another, because it takes hundreds of years and it's ongoing. It never ends. But if you look in the old records, you'll notice a point where the Latin spoken in Italy centuries ago had become noticeably different than the earlier Latin that the ancestors of French and Spanish people used to speak. And you can find the same thing in old Spanish books too, where it's not classical Latin anymore, but it's not quite Spanish yet either. We see transitional species like this in the fossil record too. We know that growing up with different languages can influence how we think about things because of how your native tongue constructs sentences, or how many words you have to describe the same thing but with more nuance than some other language has. For example, many languages use the same word for monkey and ape. So they're the same thing to those people, but not to others who may have more words to distinguish them. Now, there are interesting studies showing how different languages comprehend color differently too. For example, a Russian would look at this and see Sini and Goluboy, but I just see shades of blue. And knowing whichever language you were raised with affects how you think about things, try to imagine what it must have been like to be raised without any language at all, when physical expressions can only convey emotion or distress, and that's about it. Glances and gestures may communicate a lot, but they're not good at explaining ideas. Matters of mere animal survival don't require much thought, but how would you understand anything else? Because sometimes you have to analyze, categorize, strategize, or hypothesize things that can't be directly observed in that moment. So you have to work things out in your mind to comprehend them before you make a decision or take action, often putting thoughts into words and thinking in words with an inner monologue to explain things to yourself. But how could you do that if you don't have a concept of concepts? That's what words are. Language is the tool we use to enable higher order thinking skills. Our capability and capacity for conceptualization and comprehension was enhanced and expanded by our use of language to convey information, instructions, and ideas. It would be profoundly improbable, if not impossible, to achieve our current level of cognizance if we had no words. Speech is what made Homo sapient. Think about that. Or rather, try to contemplate that, but without phrasing those thoughts into verbiage. I bet you can't do it. And that proves my point.